what it is. So we're talking about these vector embeddings, and specifically today we're going to do examples with like words and letters, and how the vector embedding can sort of hold on to the meaning that comes from the word or the letter. And why would that be useful? Let's see what you guys say. There's many possible answers. Okay. Analysis, search, classification was a big one. Yeah, so this whole area, NLP, stands for natural language processing, and it is exactly this idea of you have something written in English, how do you feed it into like a data science system in a way that works? And this vector embedding has become like a big thing that is used in NLP a lot. So if you said NLP, that's just saying like anytime you do something like this, anytime you're processing natural language, this would be useful. But let's see some more specific things. Text classification. This is an absolutely great answer. I think probably some other people wrote classification. Classification, because it was big there. Yeah, classification. It was big on the thing. Classification. Oh, this is a great, very specific thing. Email spam classification. So imagine you have the set of words in an email, and you want to classify whether or not the email is a spam email or not. So one way is you can look directly at the words, but if you first turn the words into vectors in this meaningful way, then you can apply any algorithm that works on vectors. So for example, you could do like logistic regression just on these vectors. Let's write this down. This is a good one. So this is the use of vector embeddings. So you take your email, which is some set of words. Email equals set of words. And then you convert that into a set of vectors. And then you can apply any algorithm that takes in vectors and tries to classify. So any your favorite classification algorithm can go here. Any classification algorithm. So for example, logistic regression or random forest, anything you want, starting with the vectors rather than the words. Go to, let's say, spam or not spam. By the way, the not spam emails are called ham. Okay, spam or ham. And this is basically, you're doing a lot of great work in this vector embedding step. The computer is not working. Let's see what the problem is. Vector embedding. Okay. So the nice thing is that starting with the vectors rather than the words themselves, you will have already taken in some of the information about the words. So for example, if somebody says, I am a prince and I have lots of money to give you, a prince and large amount of money. Okay. That would be something they could say. Maybe they'll, instead of saying they're a prince, they'll say, I'm a king. Or maybe instead of saying I'm a king, they'll say I'm a queen. Or maybe instead of saying I'm a prince or a king or a queen, they say I am a rich, maybe I'll say very important person. What's another name for a very important person? Let's say a VIP someone. And the point is that if you work with the words directly, you have to have a different case for prince, king, or queen. Like these are completely different words. And so if you're starting with the words and trying to say is it spam or ham, they are completely different things, and your algorithm has to sort of separately learn, oh, okay, emails about princes and emails about kings, those are all different things, and then all of them are more likely to be spam, right? Unless you're like work for medieval times or something. But usually when you get an email about a prince, it's a scam email. But the point is, all of these things in the vector embeddings, prince, king, and queen, they have similar meanings as words, and so presumably they lead to similar vectors in the vector embedding. If the vector embedding is good, all of these concepts will lead to a similar vector. And so when you're doing your classification algorithm just has to learn the vector that goes with these types of things is likely to be spam. So you see, you've kind of combined things that are the same idea, but are different words into one vector. They all get smooshed into a similar type of vector, and then your classification algorithm has a much easier time to do it. The other thing that you can leverage is you can use a really, really big data set to convert the words into vectors. So for example, people use, this sounds crazy, but people use literally everything that has ever been typed on the internet. All of those words. So they download these, they're like terabytes and terabytes of data. Like they download all of Wikipedia. So back like 5 years ago, I used to think, oh, downloading all of Wikipedia was impressive. But they've gone from downloading all of Wikipedia, they download all of Reddit, They download any comment that has ever been posted on like Facebook, right? And they just have these like huge data sets. They have funny names for them like the pile and things like that. But you can literally use the entire internet. And so this is another big advantage, is that you can use really large, unsupervised data sets. You don't need to know anything about the data set. You just need to have lots of text. And inside that text, by converting it into vectors, the fact that these concepts are the same will come out. So sort of like in this step of doing the vector embedding, we can take things we know from English language, like prince and king are similar concepts, and then we can sort of only use our smaller email data set. Maybe we have a small data set of emails. So a small data set of emails is only used in the last step, and it has an easier time because sort of like some of the hard work of figuring out that these are related concepts has been done already for it using the large thing, and you can classify it as spam or ham just with a small algorithm like logistic regression or something. So this is a great example. Any questions or comments about this example? This is an extra good one to understand because you can do this for one of your final projects. So if you choose the final project, which is classifying recipes, you can do something like this. So you could take the ingredients. I think last time there was a recipe that had garam masala. This is a great example. Garam masala. And it had some other ingredients. I think it had like onions, garlic. And so you could go from the data set straight to the classification of what is the cuisine of the food. And I believe in this case it was Indian food. Or you could do this vector embedding thing where before, instead of doing it in one shot, get some vector embeddings of these words. And then use those, once you have the vector embeddings, you convert each of these things into vectors, then, and only then you convert it into classification. So you sort of like build a classification algorithm on top of a vector embedding algorithm. And again, why is this useful? Well, this recipe had garam masala, but actually maybe there's a very similar recipe somewhere else in the data set that has the same thing, but instead of garam masala, they say curry powder. And those are not the same words. So your algorithm, if it was just using the words, would say, okay, that's a completely different word. These two things are completely different. They have nothing to do with each other. I have to learn them separately. But if you turn them into vector embeddings, presumably the vector embedding for curry powder and the vector embedding for garam masala are pretty similar. So you get sort of a similar vector for these two concepts, and then your classification algorithm is like, aha, those both lead to Indian food, and it's learning sort of what the concepts are rather than the specific words. This is especially useful because that data set has some ingredients are super rare, right? So maybe there's in a third recipe, it says for garam masala curry powder, right? Maybe somebody wrote that, and it's like, right? Because these are just recipes, and so anybody can write any ingredients they want. Maybe this one only occurs like in one thing, right? So your algorithm would be like, well, I've only seen that one time. Like, I don't know what to do with that. But if it can sort of combine these concepts by using vector embeddings, then it can have an easier time classifying. So that's a great answer. Is classification algorithms. Any questions or comments about this one? Yeah.
Do we need to transform the target value also in vector to classify them?
Yeah, so you can do any classification algorithm you want. Presumably one would be like logistic regression, where you have, or I guess technically multinomial regression, where you have a different output for each of the cuisines. So in this situation, I think there's like 20 or something different cuisines that are in the task. So you would output a vector of size 20, and then you would do all that stuff like convert it into a log probability, calculate the loss function, all of this stuff. So this final classification thing is like all the classification stuff we've done before. You could do random forest, whatever you want. So the point is that the vector embedding, by building it in, is helping out. And actually, we've seen this already, right? We said like when we do PCA, that is a type of vector embedding. This is just a fancier version of PCA, if you want to think about it that way. Great question. Any other questions or comments about this one? So this is one possible way you could do the project. Of course, you don't have to do it this way. This is a fun one if you want to try to learn how these vector embeddings work. For this particular one, because it is words, you could go on the internet and get some pre-made vector embeddings. I'll show you an example of that in a second. So you could get somebody else's vector embeddings that they already trained on all of Wikipedia and all this stuff, and then you could start with that as their starting point and say, I'm going to use the vector embeddings I got from these people, and I'm only going to work on this classification side and make it as good as I can. Or you could say, I'm going to make my own vector embeddings, and we'll see a little bit how that works. That'll be the rest of the class today, is how to make the vector embeddings yourself. Okay, great. Let's see what other things there are. What else did people say? Okay, I think there was one here called ChatGPT. So this vector embedding step is, or autocomplete, is exactly one of the most important steps in how ChatGPT works. And again, it's the same idea, which is that the system that runs ChatGPT, it is too complicated for it to memorize every single word individually. So like prince, king, and queen, if those were all separate ideas, it would not be able to learn, oh, I'm supposed to do like something for prince, and I'm going to do something different for king, but actually they're like pretty related. So the way ChatGPT, the way it sort of compresses down the ideas in natural language is it says, okay, there's a vector that goes with prince, and there's a vector that goes with king, and the prediction of what the next word is depends only on that vector. And by doing that, it can combine concepts and learn a little bit faster. So this is another thing you can do is predict the next word. And actually predicting the next word is a type of classification where you can think of like, what is the next word? You can think of all the different words it could possibly be. There's like 10,000 words. Please try to predict the next one. And in fact, this is one classic way in the way that vector embeddings are trained is predict the next word. So this is predict. So predict. I'm going to say predict things, and example could be next word, which is technically a type of classification because there's only so many words it could be. So you could say, actually, the example I want to show you, I'm going to show you a quick little video on this stuff, and I think it starts with a thing. The goal of our model is to predict the next blank. Predict the next blank. And so the model has to figure out what goes in that yellow blank. Okay. So predict things. Example, next word. Another thing that you could predict is the other project for the final project, which is you could predict the scores of a movie. So you could have, for example, your user could be a vector. So if the user is a vector, this is a user vector, and a movie is a vector. This is a movie vector. You could have some algorithm for combining these two vectors together, and you could output what do you think the predicted score is. Predict score of movie user pair. So this is the other data set on the final project, is to do these kinds of predictions. And I'm going to show you one very simple way to combine two vectors to get a prediction, and I'll show you how that works. Of course, you can do more complicated things. So you could combine them with any algorithm that inputs two vectors and outputs a prediction. Could be linear regression, could be some neural network, could be anything else that we've talked about in the course of coming up with how do you input vectors and output a number. In this case, the number is, I think, in the range 1 to 5. Okay. And once again, you have the same advantages as before, is that maybe there's like two movies that are really similar. Okay, like there's the movie Die Hard, and then there's the movie Die Hard 2. Okay, and you would imagine that if somebody really likes the movie Die Hard, they probably also like Die Hard 2. And that's because Die Hard and Die Hard 2, don't think of them as two separate movies. When they get embedded, they should have a similar movie vector, right? So if two movies are similar, then similar users will like them. And so by condensing, saying, hey, these two movies, we learn that they have a similar vector. Therefore, we should have similar predictions for them. The vector can also encode important differences. Maybe like there's some one important difference between Die Hard and Die Hard 2. I don't know, there's some actor who's like in the first one and not in the other one. Maybe part of your vector is this component of, is this actor in the movie, right? And then users who like love that actor, maybe they get like a boost to their score. Users who like hate that actor get like a negative boost. So like differences between the movies can also be expressed in the movie vector. And so this is one way you can do it. I think when people did this project last year, the highest possible score was was by somebody who did this with an MLP, neural network in between, and had the best possible score. So this is one way to do it. Again, there are other ways to do it. This is not the only way, but this is a way to do it. And I'm going to show you how you can sort of train these kinds of things in the class today to find these vectors. This one, unfortunately, you cannot look up online. There are no movie vectors online. So people use words for all sorts of things. If you want to go this movie user vector approach, you have to know how to make it from the data set you were given, and I'll show you sort of how this kind of thing works. Okay. So that's a good warm-up of like, what are these vector embeddings useful for? We're going to see how do they work and how do you train them. Questions or comments? Okay, let me give you a quick reminder. This is a sort of a video version of what I talked about last class, but it has such beautiful animations and things that I can't help but show it to you. So this is a chapter of a 3 blue 1 brown video where they're explaining how ChatGPT works. And this is just a little section about word embeddings. It's a little chapter here that's like 5 minutes long on word embeddings. Of course, there's other things you need to do, but word embeddings are one of the important ideas. And it's like how the model is able to collect ideas that are different words with the same idea. How does it collect them together to learn about those ideas? So I'll show you this. And let me turn the light off here because this is a dark mode video. Okay. And okay, you have to just hope that it's light enough on my laptop. Okay, here we go. So word embeddings. Here we go.
Chunks and turn those chunks into vectors. I mentioned how those chunks are called.
We need to put it at regular speed, not 2x speed. Okay. So okay, here it is here are the vectors that come out of these words, and we're going to see how they work and what they do. And I'm going to pause it a couple times to tell you a couple things as we go. Okay. Oh, I don't want to go to the beginning. Oh no. Hopefully I can find where it was. Word embeddings. Okay. Now we're going to probably have to see an ad because I clicked around. Okay.
With all of that as foundation, let's dig into the first step of this text processing example, which is to break up the input into little chunks and turn those chunks into vectors. I mentioned how those chunks are called tokens, which might be pieces of words or punctuation, but every now and then in this chapter, and especially in the next one, I'd like to just pretend that it's broken more cleanly into words, producing synthetic speech just from text.
Let me start using the spacebar.
With all begin random, but find vocabulary, some list, because we humans think in words.
The thing that you have to know is that in ChatGPT, it does not use words. It does not do word embeddings. It does token embeddings. What is a token? A token is a piece of a word. So, for example, the word tokenization, instead of being one word, it has 2 tokens. The first token is the word token. Okay, that's like a terrible example. But the second half is ization. Ization is not a word, but it is a token, right? And every word is made of lots of little tokens put together. Some tokens can be as short as just one letter. Some tokens are full words. And this is something that is needed to get like the best possible performance out of ChatGPT. Of course, the idea works perfectly well with just words. And in fact, a lot of these things were done with word embeddings. There is no reason for you to do anything that involves tokens in this course. So totally fine to do it with words. And you're going to see all the examples that have words now. Okay.
Words, this will just make it much easier to reference little examples and clarify each step. The model has a predefined vocabulary, some list of all possible words, say 50,000 of them. And the first matrix that we'll encounter, known as the embedding matrix, has a single column for each one of these words.
Okay, so far I've always said you think of each word as a vector. Of course, if there's 50,000 words in your vocabulary, you can stack all the vectors together to make a big matrix. That's called the embedding matrix. But I mean, equally well, you can think of it as a bunch of vectors. I think that's just as good for thinking about it.
These columns are what determines what vector each word turns into in that first step. We label it WE, and like all the matrices we see, its values begin random, but they're going to be learned based on data.
Okay, so this is the way things always work in machine learning, is we start out, all of the numbers are random numbers to start out with, and then over time we train them with gradient descent to make them do what we want. Okay? In the case of ChatGPT, do what we want means predict the next word. In the case of your final project, you might be predict if it's Indian food or Italian food, or it might be predict the user scores. So either way, you're making the numbers do what you want through training on some loss function. Okay.
Turning words into vectors was common practice in machine learning long before transformers, But it's a little weird if you've never seen it before, and it sets the foundation for everything that follows, so let's take a moment to get familiar with it. We often call this embedding a word, which invites you to think of these vectors very geometrically, as points in some high-dimensional space. Visualizing a list of 3 numbers as coordinates for points in 3D space would be no problem, but word embeddings tend to be much higher dimensional. In GPT-3, they have 12,288 dimensions, and as you'll see, it matters to work in a space that has a lot of distinct directions. In the same way that you could take a 2-dimensional slice through a 3D space and project all the points onto that slice, for the sake of animating word embeddings that a simple model is giving me, I'm going to do an analogous thing by choosing a 3-dimensional slice through this very high-dimensional space and projecting the word vectors down onto that and displaying the results. The big idea here is that as a model tweaks and tunes its weights to determine how exactly words get embedded as vectors during training, it tends to settle on a set of embeddings where directions in the space have a kind of semantic meaning. For the simple word-to-vector model I'm running here, if I run a search for all the words whose embeddings are closest to that of tower, you'll notice how they all seem to give very similar tower-ish vibes. And if you want to pull up some Python and play along at home, this is the specific model that I'm using to make the animations. It's not a transformer, but it's enough to illustrate the idea.
Okay, so this is the GLOVE dataset. GLOVE is an acronym that stands for like general something. You see it says -wiki. This was trained on Wikipedia. So this is a model from like 10 years ago. It is better than the one you saw before called letter2vec, which was an earlier model. So this has like a different way of training, but it's the same kind of idea. It's trying to predict which words come near other words, okay? And so words like words like building and tower have similar embeddings because any sentence that has the word tower in it, you can delete tower and replace it with building, and the sentence is sort of like equally likely to appear. And so that's how it works, and it's trained on Wikipedia. Okay, and I believe the -50 means the words are 50-dimensional vectors. So you can download they have different packages with different sizes of vectors. If you want to use a pre-made vector embedding, for example, for words like garam masala and onion and stuff, this is a nice data set to use. I'm sure there's more modern ones that are even better, but this is like a very classical one that lots of people have used, and it's like known to be good in a lot of contexts. How high the dimension should be depends on what you want to do. So I guess for these examples, they're doing 50-dimensional stuff. Questions or comments about this stuff? Okay, let's keep watching the video.
That directions in the space can carry semantic meaning. A very classic example of this is how if you take the difference between the vectors for woman and man, something you would visualize as a little vector in the space connecting the tip of one to the tip of the other, it's very similar to the difference between king and queen. So let's say you didn't know the word for a female monarch, you could find it by taking king, adding this woman minus man direction, and searching for the embeddings closest to that point. At least, kind of. Despite this being a classic example, for the model I'm playing with, the true embedding of queen is actually a little farther off than this would suggest, presumably because the way that queen is used in training data is not merely a feminine version of king. When I played around...
This is a good point, is this king, queen, man, woman analogy was originally invented in the word2vec dataset. And he's using the GLOVE vectors. So I think that's why he's not getting it as classically as he could. He's using the wrong embeddings, and I guess in this embedding on the Wikipedia dataset, the word queen is slightly different than just a female version of king. But okay, let's see some more examples.
Family relations seem to illustrate the idea much better. The point is, it looks like during training, the model found it advantageous to choose embeddings such that one direction in this space encodes gender information. Another example is that if you take the embedding of Italy and you subtract the embedding of Germany, and then you add that to the embedding of Hitler, you get something very close to the embedding of Mussolini. It's as if the model learned to associate some directions with Italianness and others with World War II Axis leaders.
See, okay, this is a great example, I think, where if you were making a spam embedding thing, right, and somebody types in Hitler or somebody types in Mussolini, you sort of want to treat those as the same. So somehow, how Italian or German something is irrelevant to is it a spam email or not. But does it involve World War II, like dictators? That might be relevant. So sort of like this is a good example of showing how the model is taking ideas in the words and putting them in separate directions, And then anything you build on top of that can take advantage of that fact. Okay, let's keep watching.
Maybe my favorite example in this vein is how in some models, if you take the difference between Germany and Japan and you add it to sushi, you end up very close to bratwurst. Also, in playing this game of finding nearest neighbors, I was very pleased to see how close cat was to both beast and monster. One bit of mathematical intuition that's helpful to have in mind, especially for the next chapter, is how the dot product of two vectors can be thought of as a way to measure how well they align. Computationally, dot products involve multiplying all the corresponding components and then adding the results, which is good since so much of our computation has to look like weighted sums. Geometrically, the dot product is positive when vectors point in similar directions, it's 0 if they're perpendicular, and it's negative whenever they point in opposite directions. For example, let's say you were playing with this model and you hypothesize that the embedding of cats minus cat might represent a sort of plurality direction in this space. To test this, I'm going to take this vector and compute its dot product against the embeddings of certain singular nouns and compare it to the dot products with the corresponding plural nouns. If you play around with this, you'll notice that the plural ones do indeed seem to consistently give higher values than the singular ones, indicating that they align more with this direction. It's also fun how if you take this dot product with the embeddings of the words 1, 2, 3, and so on, they give increasing values, so it's as if we can quantitatively measure how plural the model finds a given word.
This is another great example, I think, for the classifying the type of food. Does it matter if it's onion or onions in the recipe? Probably not. So, like, by having this direction in the data, in the vector embeddings, that is it plural? You know that direction is going to be irrelevant in the final thing, right? Whether it's onion or onions, your model can learn, hey, these are the same concept, and the only difference is this plural direction. And then somehow in the next part of your model, you build in something that will learn, hey, the plural direction doesn't help you classify the recipe. Just ignore that part. Focus on the actual rest of it. So this is another great example of how you can extract useful things in using these vector embeddings.
Again, the specifics for how words get embedded is learned using data. This embedding matrix, whose columns tell us what happens to each word, is the first pile of weights in our model. And using the GPT-3 numbers, the vocabulary size specifically is 50,257, and again, technically this consists not of words per se, but of tokens. And the embedding dimension is 12,288. Multiplying those tells us this consists of about 617 million weights.
Okay, so this is how the GPT model works, which is like part of how ChatGPT works. This is from GPT-3, which was when GPT was released in 2021, like 3 years ago. This is the model that they used. And so it has this many parameters, 600 million, just for the embeddings of all the different tokens that can come in. Of course, when you do this stuff, you'll probably have things a lot smaller. There's no reason to go up to 12,000 dimensions for each word. And for example, if you're doing the food data set, you just need one vector for each of the words that appear as ingredients, which I think there's several hundred of, not 50,000. So yours will be a lot smaller. And in the rest of the class, I'm going to start off with an even smaller example, is we are going to do letter embeddings. We're going to do letter embeddings. So in the rest of the class, we're going to learn how these vector embeddings work by doing letter embeddings. Okay, so what I'm going to do is I'm going to start with letters. You know the letters, A, B, C, all the way up to Z. And I'm going to try to find an embedding of these letters. So I'm going to try to do a vector embedding and show you all the details of how this works. I want it to use it for a certain task. So I'm going to train it on that certain task. And the task is predicting which letter comes next in a name. Okay, so for example, if you have the name, the common name, EMM blank, we would want to use the vector embeddings of these letters EMM to predict that the next letter is supposed to be A, Emma. It's the word Emma. So that's what we're going to do. And so the first thing we got to decide is how are we going to input these vector embeddings, and what is the output going to be? So my task is going to be inputting some letters. It's going to do some vector embedding, and it's going to do something to try to come up with this thing. And I made a little mathematize for you to see if you can predict how is it going to work, sort of at a very high level. What are the inputs and the outputs going to be? And that is the next thing over here. So The input will be a vector of size blank, and we turn input letters into that using blank encoding. So we're going to do some kind of encoding of the letters, and we need to make vectors. And the output is going to be a vector of size blank, and we interpret the outputs as probabilities by using blank. Okay, you guys got to fill in the blanks. So these are kinds of things we've done before that we're, again, combining now to see how they work. Okay, I'll give you a minute to try to fill this in. And there's a little write-up over here. So we're doing letter2vec, which finds vector embeddings of letters, and that's how it's going to sort of work. And here's the task: given the current letter, predict what the next letter will be. Okay, so I'll start a timer.
But the word has a number in between, so how do you know?
Sorry, what was that?
The word letter to vec.
Oh, letter. Why is it a 2? Yes, because if you write the word 2, then your brain cannot see where the words are. So then it would be like letter2vec. So you put a 2, then it just looks like 2. I don't know. Okay, I'll tell you the actual truth. I got this example from this guy Andre Karpathy, who does these things, and he made exactly this kind of thing. He calls it Make More, and it's this really great tutorial series where the final video is a 4-hour-long video where he programs GPT-2 from scratch. So starting with like a blank, empty thing, he programs everything. This guy used to be the head of AI at Tesla, and he was one of the I don't think he was a co-founder, but he was one of the first people who worked at OpenAI. So he's like a really big shot machine learning guy, and I don't know, for whatever reason he thinks it's really fun to make YouTube videos. So it's pretty amazing the stuff he does. And I took this example from building Make More Part 2, so he calls it Make More, and this is where the letter2vec thing comes from. Okay, we'll have more on him in a second, but that's where the name comes from. Okay, let's see, how are we doing on answers? Only one answer so far. Let me give you another 30 seconds. Again, feel free to take a guess. It's totally fine if you don't know. It sort of helps me figure out how quickly to go over things. Do you know how to convert the outputs of the network into probabilities? We've done that. Should I go over it again slowly, or should I go over it again quickly? Sort of depends on how many people get it right. Okay, time's up. Put in your final guesses. I know we only have one answer. Put in whatever you think, and we'll see what people said. Okay. I guess I have to give people a final time. 10 more seconds, and then I'm going to stop the madness. Okay, let's do it. What did people do? Or what did people say? So, the input is a vector of size 26. That is the right answer. So, why is the input a vector of size 26? It's because there's 26 possible letters, and you think of them. So you think of the letter A, you think of that as the vector 1, 0, 0, 0, 0, 0. You think of the letter B is the vector 0, 1, 0, 0, 0. And then when you do a vector embedding, what that really is matrix multiplication. So let's call this thing VA. Let's call this thing VB. Actually, I shouldn't call it V, because we're going to have vectors later. Why don't I call it OO of A, and this is OO of B. What could OH, I meant to say OH. OH of A and OH of B. What is OH? That is the answer to the next blank. Let's see how many people got that. We input the letters by using the blank encoding. One hot, very good. Some people did it with a dash, some people did it without a dash, but it is the one hot encoding. So you can take the things and just very mechanically turn them into one hot vectors, and then you can get the vector embedding by doing matrix multiplication. So if you have a vector embedding matrix, then it's going to be 26 by whatever dimension you want. So this is the embedding dimension. And then you can get the the embedding by doing matrix multiplication. Do I want it the other way? Actually, okay, let's see, what did I do in the code? Let's go to the code and just see what I did. So downloading, this is our data set. Emma, you see Emma's the first example. And what did I make the size of the matrix? Okay, so I made it. This V is 27 by the embedding dimension. So 27 by the embedding dimension. You might notice 27 is not the same as 26, which is the number of letters. That's because there's one extra character, which means this is the end of the word. So there's 26 letters, plus there's period, which means stop making the name. Okay, so yeah, so it is 26 by the embedding dimension, and then you get the vector. So the vector embedding of A, the computer is taking its time. Okay, it's doing something weird. It doesn't like me. Okay, equals the 1 hot of A. This is the problem with technology. A regular pen. Okay, times the matrix M. So the matrix M sort of stores everything in columns and rows, and then to extract the vector embedding, you pick out the right column of M by using these 1 hot embeddings. So that is the input, and you could represent this input as a neural network picture like we did before. So you could have, these are the 26 inputs, and then you have this hidden layer in the middle, and then the matrix M, the embedding matrix, is connecting the inputs to the thing. And the vector for the A is the vector of all the weights that connect from the first neuron, and the vector for B is all the weights that connect to the second neuron. So this is what we saw with our neural networks. Let me write M up here. So that's the first half. That's the input. What is the output? The output is going to be all the way over here. So thinking of it as a neural network, it's a neural network where the first layer is 26, and we think of it as 1 hot, and the output is what? Let's see what you guys said. I want to go here. The output is a vector of size, also 26. So 26 is correct. Why is the output size 26? Well, the reason is I want it to output letters. And so what I'm going to do is I'm going to make it output the probability of each letter. So the output is, again, 26. So this will be the probability that the output equals A. Will be some output over here. Then there'll be the probability that the output equals B, and so on. And this is the probability that the output equals Z, the last letter of the alphabet. So it's a vector of size 26 because there's 26 possible outputs. How do we go from whatever's going on in the network to these probabilities? That is another common step. This is always used in every machine learning model ever, basically. We interpret the outputs of the network as probabilities by using softmax. Activation functions go in the middle, not at the end. And let's see. Cross entropy is part of how we train it, but the end bit of every neural network that outputs probabilities is always a softmax. Which is, again, very similar to the logistic function. So these things really come from a layer, which is the logits, which looks like this. And to get from the logits to the log probabilities, or the probabilities, you do the softmax function, softmax. And then that is exactly the same as a previous class. So the formula is the probability that we output the thing number I. Well, let me write it out in a little more detail. The output equals I thing is equal to the logit number I, and then you take it to the e to the power of that, and you divide by the sum over all the other logits. Logit j going from 1 to n. N is 26 in this case. And that's the softmax function. It says take the logits, exponentiate them, and divide by the sum, and that will give you the probabilities. Okay, so this is what every type of neural network that does this kind of task would do. This would be the vector embedding, and you could fill in whatever you wanted here. And again, what is the advantage of having a vector embedding? Like, why am I thinking this is a vector embedding? It's because my model will learn that similar letters actually represent similar concepts. So for example, the letter E and the letter A are both vowels. Maybe they have a similar vector, and whatever we learn about A will transfer over to learning about E. So that's the advantage of thinking of it this way. So in principle, you could do anything you wanted in between. The input and the output have to be like this. But the simplest possible thing you could do is let's take the matrix M and put it on this side as well. So let's just do, we have the matrix M. We put the reverse of the matrix M. So this is right. This is 26 by embedding dimension. What could we put over here to connect the embedding dimension to something which has 26 things? Let's just put M again, and just put it in reverse. So if you put M transpose is something that is embedding dimension by 26, and that will perfectly fit to connect the input to the output. So this is the simplest possible thing you could do. You have one matrix M, and you are putting it in twice. And I will tell you this has a very cute interpretation, which is that the probability that the output equals I given the input equals J, let's say the jth letter, the ith letter. So by using the same matrix on both sides, this will be just the dot product. It'll be the dot product of the vector I with the vector for J. So if you go through the math of what this means, so first you do M of the thing, that is the vector I. So this MVI, this is M times what the 1 hot of I. This VJ is M transpose, well, okay, it's M times the 1 hot of J. And what is VI times VI transpose? It's exactly 1 hot of I times M times M transpose 1 hot of J, if you do it correctly with the right transposes. I guess it should be, this thing should be on the other side. The 1 hot is over here, 1 hot of J. But in any case, it's the inner product. So what's going on in the network is the logit will be precisely just the inner product of the things. Okay, so what are the probabilities? The probability is not just the inner product. The probability will be e to the power of this inner product divided by the sum over all the letters. So e to the vi, let's say vk, k going from 1 to n. So this is the model. We have this matrix M that stores all these vectors, those columns, and we're trying to find the embeddings so that the output of letter I, given the input was letter J, is e to the vi vj, and we try to tune the vectors to do what we want. So that's the model, and it's like the world's simplest vector embedding model that you can do for this letter task. That's exactly what I did. So I'm going to show you that in a second, but are there any questions about the high level, like the picture, or what's going on over here? Yeah?
So here we are dealing with letters, so what in case if we have numbers in the pizza
What if there were numbers and letters? Then you would have to add in any type of input or output you want, you would have to add in. So if it was letters and numbers, you could do 26 inputs for the letters, and then you say 10 inputs for the digits 0 to 9. You could do like 2-letter chunks, right? You could say like, I'm going to predict the next 2 letters given the first 2 letters, and you have 26 squared inputs. Maybe you have 100 inputs for the 100 most common ingredients. So whatever you want the inputs to be, you put them as individual inputs with 1 hot embedding, and whatever you want the outputs to be, you put them as outputs. It's a great example. Yeah, great question. Yeah, I guess let's do the 2 examples. While we're thinking of inputs and outputs, let's do the 2 examples of the movies, and let's do the ingredients. So ingredients, so the input size would have to be the number of ingredients, of possible ingredients, right? You'd have like a neuron for every ingredient, and the output size would be the number of different cuisines, right? Number of different cuisines. So this is like if you want to predict using only one ingredient what it would be. You'd have to make it a little more complicated to do multiple ingredients, but this is like essentially what you're doing. So your vector embedding is going to be this matrix with that input size. And for the movies, the input size would be like would be like the number of movies in the data set. What would be the output size? Does anyone want to take a stab? This one's a little different. What would be the output size for this one? So this would be like if you're given the movie, you want to predict what the score was, which is a little silly. You got to involve the user somehow, which I don't have that in there yet. So just ignore that. But the output size for this task, what is the output size for the task? Yeah. What do you think it is? 5? Yeah, that's one possibility. So if it was 5, you're like, what's the chance it's a 5-star? What's the chance it's a 4-star? What's the chance it's a 3-star? What's the chance it's a 2-star? You could do that, but remember, you are just being graded on how close you are to the final answer. So if you want to predict the individual probabilities, then you have the job of combining the probabilities into a final guess. And you don't necessarily want to do the most probable one, right? If it's somewhere between a 4 and a 5, you want to guess like 4.5. So if you're doing 5, you're doing classification of is it 1-star, 2-star, 3-star, 4-star, 5-star? Try to get that as accurate as you can. But there's something else you can do instead of 5-dimensional. Anyone want to take a guess? It's simpler than you think.
Vector.
A vector. A vector is 1-dimensional. So you could just do a 1-dimensional output. So this would be if you want to classify. This you would do 5 because there's 5 categories. But you could just do just 1, and that would be just what is the value? What is the value? And in this situation, it's extra easy because you just do the mean squared error on this one output. So the whole network does some funny thing. It inputs the movie, does a whole bunch of computation, and then it outputs, I think it's a 4.3-star movie. And then you do mean squared error on the actual ratings. So it could be 1-dimensional output, and that's because you're not doing classification. I will show you, by the way, before we get to the end of class, I will show you how to incorporate the users. So right now, this is really kind of a fun example because I only have the movie. You got to somehow include the user. We'll see what that looks like too. Okay, but let's go back to our letter2vec example. And so we're going to try this model. So we're going to try to find embeddings of letters so that the probability of the next letter coming up is this inner product. Or more accurately, the logits are the inner product, and the probabilities are the softmax of the logits are this e to the power thing. Okay, let's see what this looks like in the code. And all of this code is based on this video that I told you about. It's based on building Make More Part 2, where he does a complicated version of this. I'll say what he does in a second, but all the code is taken from there and modified to be a little more simple. So if you want details on how it works, you can see all of this stuff. Okay, so let's see, how does this code work? So on purpose, we're going to try to find these probabilities. So the probability that the letter k plus 1 equals a, given that the previous letter was b, is e to the va inner product with vb. This little proportional to means divide so that it's the sum is 1. And how does it work? Okay. So at the beginning, we're just downloading the data set. So the data set is a list of baby names. So Emma, Olivia, Ava, Isabella, Sophia, these are names. I think they're in order by gender. So the first half is all the girl names, and the second half is all the boys' names. But there's 32,000 names in this data set. I think this was like the most common baby names of 2023 or something. Okay, and here's the data set. We're encoding everything using letters. So there's a Python dictionary that says A is the letter 1, B is the letter 2, and there's one special thing that I told you to watch out for, which is that at the end, 0 is dot, and dot means end of the name. So the word Emma is actually Emma dot, is like the baby name is Emma, and that's it. There's no more. And I think there's a little example over here. So this is the data set. Does it tell me what it looks like? Okay, so these are, what are these data sets? These are, take the words, which are names, and convert them into sequences. So Emma becomes E, then M, then M, then A, then dot. And so that's what is getting encoded in these X and Y matrices. And then we split them into a test set, a training set, and a development set. So the training set is size 182,000. 182,000 is a lot bigger than the number of baby names because every baby name gets turned into a bunch of letters, right? So this is sort of like all of the letters in order. And I think the next thing we have is a little example here with Emma. Where's the example with Emma? Okay, hold on. I'll get the example with Emma. give me one sec. I guess we have to find it in this guy's thing. Is he going to show me Emma? Oh no, what a disaster. Oh, here we go. Okay, yeah, great. Look, I stumbled upon exactly what it is. So the baby named Emma, let me see if I can make this extra big. Full screen, and then can I zoom in even more? Okay, hopefully you guys can see this. So the baby named Emma becomes the sequence EMMA dot, and then when we feed it into our network, it's going to be like, given E, you're trying to predict M. Given M, you're trying to predict the next M. Given M, you're trying to predict the next A. Given A, you're trying to predict dot. And so that's our training examples are the pairs E then M, M then M, M then A then dot. And so our network is going to try to use that formula to predict the probabilities, and then we're going to build a loss function, which is the cross entropy loss, and train it using these sequences. So that's exactly what is being done. Okay. You guys with me so far? Any questions or comments? Okay, let's see how the code actually works. So I made the embedding dimension 6. You can change this to anything you want. Of course, if you make it very big, it has a lot more room to learn with, but maybe it spreads things out and will start to overfit. So there's a balance to be had. This is like a hyperparameter you would tune by trying different values and seeing what is the best. So I went with 6 dimensions, and this V, this vector V, is exactly the embedding matrix. So it's 27 by 6, so 6-dimensional inputs, and VA is the vector for letter A. Okay. What are the parameters in this model? It's just this matrix of all these things. Those are the only things. If you have these vector embeddings, you can find the output because the inner product is VA with VB. Okay. When you use this thing called PyTorch, which is what this is trained in Torch, you go through the parameters and you say, I would like to do gradients with these things. So please turn on the gradients. That's what this requires gradient thing does. When we do gradient descent, that's what it's going to do the gradient with respect to with these parameters. Okay. How does the training work? These things are just writing down the loss function as we go. We're going to loop through and do 30,000 training steps. At every training step, we're going to have a batch of size 256 examples, and we're going to use those 256 examples to calculate the loss and then update our things. Okay, and here are our examples. So it's the V of the training set. And here is the function for the predicted probabilities. And you see it's a very simple one-liner, and that's because our model is so simple. This at symbol is matrix multiplication. So what it says is to figure out the logits of the output, take the embeddings of the input, X embeddings, of the examples you're working with, and matrix multiply it with the vector output. This is the one-line, simple matrix multiplication version of this little picture that I set over here, is that the inputs are some embedding, and then the output you multiply by M transpose. That takes you to the next thing. So there's no nonlinearity, nothing fancy here. Just doing matrix multiplication, it's essentially M times M transpose. And that's what's going on here. M is called V, and that line is doing it. So that is doing the predicted probability logits. What is the loss function? And in the past, we wrote the loss function all by hand, but if you do the torch package, there's a function called cross entropy, and you just give it the logits and the actual answers, and it computes the cross entropy. So this is like what we did last class. It's computing the cross entropy loss of our predictions with the true answers, which is a Y training of the examples we picked. That's the loss function. Is this more or less? This should be like building on the previous things we did. Questions or comments about any of this stuff? Once again, you can watch the video as well, where he does lots of examples. It's a nice long video, which is great because like there's no details skipped. It really is from scratch, writing everything and how it works. Okay, then we do the gradient. So how do you do the gradient? Well, you set the derivative of everything to 0, and you use this function called loss.backward. Loss.backwards means do the gradient of the loss function and tell me in every single parameter, write down in p.grad what the gradient was. So this is a funny way of doing the derivative. It looked a little bit more normal in what we were doing before because we were using the JAX package, and this is using PyTorch. But this is doing the derivative. For technical reasons, in machine learning, people call doing the derivative, they call that the backwards pass. That has to do with how it's computed. When you compute it, you're doing something backwards. But what you're doing is calculating the gradient. The backwards is how you're doing it. But for whatever reason, people call it the backwards pass. So that does the gradient. And then we just update the each of the parameters. We update it by subtracting the LR times the gradient. What is the LR? The LR is the learning rate. And the learning rate is on a little schedule here. For the first 100,000 steps, it's 0.1, and then it switches down to 0.01. That's just like a fancy way to make your training better. But this is doing gradient descent. And this guy was clever enough to include the minus sign that I always forget. So he's doing really gradient descent, making the cross-entry loss smaller. If you forget that minus sign, nothing will work. Okay, then we write down what we did. So we write down our scores, and then we do it. And I ran it this morning. It took 23 seconds. Okay. Here is what the loss function looks like during training. So we start out with a totally random thing. Our loss is like 3.15. If you do e to the power 3.15, it should be close to 27. All right, because there's 27 possible characters that you're picking randomly to start with. Your cross-entry loss is e to the 3.15. But then as we train, it gets better and better. So it goes down and down. That means we're getting better at our predictions. And it goes down to a minimum of around 2.8. 2.8. So pretty good. All right. And here it is testing the loss on the training set, the test set, and the dev set. And you can see it's always around 2.8. Okay, very good. Now is the fun part. We get to visualize the results. And what I'm doing is I made a graph of the vector embeddings of the letters. Of course, the graph can only be two-dimensional. My embeddings are six-dimensional. So how did I convert from 6 dimensions down to two dimensions to graph it? I use PCA. So this is the top two PCA directions. And these are the vectors that the letters got mapped to. And you can see something a little bit interesting already, which is that the vowels all tend to be over here. So I and E and O and U, they are all kind of over here. A is a little bit different, it's over here. And then we have this like sequence of letters like P, S, W, G, T. Those kind of play similar roles in names. There's one weirdo letter who's far away from everybody else. Do you guys see the weirdo letter? Q is like shun. Get out of here, Q. We hate you. I guess the other weird letters, C, K are very close together because C and K are similar. H and J, they are all in one little group. That's when I ran it this morning. It has a different, on GitHub, there's how I ran it the other day, and it looks a little different. What does it look like? Q is still over there, and this time, maybe it's the same? Okay, well, in any case, there we go. Okay, and then this is the really fun part. We can write out all the different predictions. So in this case, there's not so many. We can write them all out, and we can see what our model assigns as the probabilities for the next letter. So, for example, our model thinks that after, this is the Q row, so after a Q, it says you should stop 6.5% of the time. After a Q, you should put a U 10% of the time. And that's the largest value in this row, is this. After a Q, the most likely letter is U. Very good. What is the most likely letter after an N? Apparently, another N. Do an N, what's going to come after the N? Another N. After an L, another L. So the dark values are the most likely things. Every single row adds up to 100%. And that's how it's working. All right. And then this is the fun part. You can make names. So here is us making some names by using this thing. So we start out with nothing, and then we predict the next letter, and then we just keep predicting letters over and over again. And at the end, it says at some point it says to stop. So these are examples of names that our model generated. You can see it's working very well. Here's a name, Nana Joya. Joya, if we cut out that first part, that's not bad. Near Shikarin. I like this one, D. So, okay, is this model working great? I would say no. Oh, Ron. Hey, that's a real name. There we go. Success. Okay, so these are some names. Question, yeah. Okay, so, oh yeah, Noi Tasha. Look, that's pretty good. Okay, so why is this model doing not very good? One reason is it's a little bit too simple. So first of all, it's only using one letter at a time to predict the next one. So that's one major thing. But there is another very simple improvement you can make to this model, almost exactly working exactly as is. You can make one small change and make it a lot better. And the very simple thing is, right now, I'm using the same vector v for both the input and the output. So in other words, I have the input is some letter, and the input is some other letter, and I'm doing the same vectors v for the input and the output. And in particular, this basically means that the probability you get the output is I when the input is j is the same, essentially, or is like related to the reverse. Input equals j, given output equals I. They're both related. And so, for example, if you look at QU, like I gave this as an example. I said QU is the most likely letter to come after Q is U. And the model did that by increasing the weights to make the inner product of Q with U very large. So it says, whenever I see a Q, there's so many U's coming after it, I should make the inner product of the letter Q and the letter U as high as possible. But if you make the inner product of Q with U very high to make QU more likely, you also make UQ more likely, like the reverse. So if we look over here, we should find that UQ is pretty likely. Let's see, is it true? U followed by dot, UQ is only 0.8. So it's not too high, but probably higher than what it is in the real data set. So, and this is a limitation of the model. Another place you'll notice this is that it likes to put double letters, right? And that's because double letters are the inner product of a vector with itself. That's as long as the vector can be. So it likes double letters a lot more than it should, just by the geometry we're using. So a really simple way you can fix it is, let's just use a different vector embedding for the output than the input. So all we're going to do, very simple improvement, we're just going to say, let's add a new vector embedding. And I think the way I did this is I called this one W. So instead of having just V, let's have two embeddings. An embedding for the input and an embedding for the output. And then you can combine them by doing the inner product of VI with WJ. And that way, any given letter is treated sort of as a different entity if it's the input letter or the output letter. So first letter Q is completely different than second letter Q. OK. Let's see what that looks like. So that's the next idea. With two vectors. So all we do is we have two vector representations. There's the input representation, there's the output representation, and we kind of think of these as two separate things, and that is just equivalent to having two vectors, V and W. The code is almost identical, so the only difference is I have a V and a W. Before I only had a V, and then so one is the input, the V's are the inputs, the W's are the outputs, and then everything is the same except for over here, right? I get the embeddings with V, so that's the input, and then I multiply by the matrix W. That's the output. So the V and W are different outputs. And now, when you run it, you have, first of all, you can see the result is better because instead of being 2.8, which is way up there, it's 2.5. So that's very good. Nice improvement. But second of all, you can see that it's better by plotting the words again. So now we have two plots. One is the input and one is the output. And you can see it's doing a much better job of, say, grouping the vowels. So O, A, E, and U as inputs are all very similar, right? The letter that comes after a vowel is like pretty similar no matter what the vowel is. As over here, here are the outputs, and you can see, I guess H is a weird output. What else is a weird output? Q is a weird one over here. Where is Q over here? I guess Q should be shunned over here. J is shunned, and Q is all the way up here. And now when you do the outputs, it looks a little bit better. I guess we have that matrix again. So the matrix now should be a lot more realistic. And now you see QU is now 70% likely. So after a Q, you're almost guaranteed to have a U. Everything else is not really possible. I guess there's an 11% chance your name ends in a Q. The Q is, your name is something Q dot, and then you finish. And so it doesn't, we've sort of removed the bias towards double letters. We fixed this Q thing. Things are working a lot better. And here are some example names that you get, which hopefully look a little better than before. This one, you see the model can sometimes just decide to keep going and going. Let's pick a good one. Hey, that's a nice name. Ella Levenlien. That could be a name. Me. Hey, that's like the first two letters of my name. That's great. Kara. There's a famous chess guy named Kara. He invented an opening called the Karo Khan. Okay, great. Lineal. These are fantastic. Okay, so what is the moral of the story? We improved it by changing the architecture a bit and having 2 embeddings. Why is this important to you? This solves the problem of the movies. So the movies, how do I get the, how do I do the movies? I think I had somewhere here. I was trying to do the movies and it didn't make any sense. Yeah, okay. So the movies, instead of having one input, which is the movie, why don't we have 2 vector embeddings? We have a movie embedding and a user embedding. The input size for the movies, this is the movie embedding. And you have a different input, which is the input for the user size, is the number of users. This is the number of users. And the output can still be size 1. And in fact, the output, what the output can be, it can literally be the inner product of vi with wj. So this is the prediction for movie I with user j, is we take the inner product between how much vector I works with wj. And if they're kind of aligned, then this is a high number. If they're anti-aligned, this is a very low number. This, of course, outputs a number between minus infinity and infinity. To make it a number between 0 and 5, why don't I do e to the power of this divided by 1 plus e to the power of this. So this is the softmax function, and that'll be a number between 0 and 1. So to make it between 0 and 5, I'll multiply it by 4 and add 1. So there we go. So this says how much we predict movie I is liked by user j. We take the vector embedding vi, we do the inner product with wj, and we scale the inner product so that's between 1 and 5. And if you do this, you can make it work. So this is the output. You train it with mean squared error. This is one possible way to do your final project. If you want to learn how to do these kinds of things. Of course, if you want to stick with the classical data science stat stuff, also totally fine. So this is just if you want to learn how to do these things, you'd have to read the code and try your own examples and make the gradients flow and do the gradient descent. Okay. Question, yeah?
For the movie example, would we get to see what the high score was?
I can tell you. Yeah, sure, I'll tell you. I'll look it up and tell you. It is a bit tricky, and you can't get it extremely, extremely good. So there's quite a bit of like noise in the data set. So movies and users are different enough that like even the best possible prediction is not that great. I will tell you guys what the ceiling is. Yeah, that's a great question. And for the ingredients one, of course, there's a public leaderboard where you can go see how other people are doing. Okay, so that's how to do the movies and users with 2 vectors. How would I combine multiple ingredients? So in this little thing, I said you only have 1 ingredient. How do you combine to get multiple ingredients? Well, the answer is you can stack them on top of each other. So what you can do, and that's shown in this picture from the video. So over here is a picture. This is the paper, the academic research paper that he's implementing, and it's showing you how to stack them. I have that paper over here. It's from 2003, so it's like 20 years old. And what they're doing is you embed, so this is how you combine 3 different words together to get the output. And so what they're trying to do here is use the last 3 words to predict the next word. They use a vector embedding for all 3 words to get a stack of 3 times the size of the vector input. And then they do some machine learning stuff. They do some arbitrary stuff here. Here they're using the tanh function. They have 1 hidden layer. And then they use softmax to get the probability. So the final probability is the output is from a softmax. And that actually is exactly what is implemented in this video. So in this video, he predicts baby names by using 3 letters to predict the next letter by stacking them up into a vector by taking 3 vector embeddings and stacking them up. Actually, let me show his code. I thought I had it, but I might have to use the link here. Jupyter Notebook, great. Okay, so this is his code. So he's using, how many characters does he use? I was only using 1 letter to predict the next letter. He uses 3 letters to predict the next letter, which makes his model a lot better than mine. But it's taking these things and stacking them together. Okay, and his his loss is much less than mine. Remember, my loss was like 2.5. His loss is like 0.4. So by using 3 letters to predict instead of 1, you use the vector embeddings 3 times, you can get a much better thing. But I believe he has a picture. This is the picture of his letter embeddings. And you can see his letter embeddings are very nice. A, E, I, O, U, nicely curtailed over here. Q, shunned in the corner over here. Beautiful. Letters that are similar are put together. Okay. And the best part is these are the predictions. These are the new letters. So these are some really good words, names. Melarara, Jose, Quinton, Lilia, Jamilio. That's a good one. That's a good name. Okay, so hopefully you kind of vaguely see how these vector embeddings work and how they're useful. I think this is one of the most powerful ideas in modern machine learning. I'll have a bunch of links for you, some of which you've seen already. If you want to get into this stuff and learn how to do it, it's an exciting time to learn these things. And so you should definitely feel free to try it for the final project if you want to. You can also stick to some of the classical things if you think this is a little too spicy for you. That's also fine. Questions or comments before we stop? Okay, let's stop there. On Friday, you should submit your project 2 and make sure you pick